Enumerative combinatorics is founded on the 3 principles that I mentioned in the previous video. This video is to explore these principles in detail. Even if you are familiar with combinatorics, this video will revisit those concepts very clearly, so it will be worth your time. Addition principle is to come up with different distinct approaches to solve the same task. You either choose the first approach, or the second one, or the nth one, and only one of them. We now denote the number of ways to do the task using the first approach as A1, the second approach as A2, all the way to AN. The addition principle tells us that we need to add these numbers up to get the total number of ways to achieve the big task. The multiplication principle is to break the big task into different subtasks. You have to go through the first subtask, second subtask, all the way to the nth one, and all needs to be done. We now denote the number of ways to do first subtask as B1, the second subtask as B2, all the way to Bn. The multiplication principle tells us that we need to multiply these numbers up to get the total number of ways to achieve the big task. The inclusion-exclusion principle is pretty similar to the situation of the addition principle, where you need to choose one approach out of many. However, the approaches are not distinct. There could be overlapping areas. This is because there could be some ways that can be classified under different approaches. We use A12 to denote the number of ways in the overlapping area. Then we need to subtract A12 to offset the overlapping area. Of course, we also have the overlapping area between the first and third approach, and so on. However, for those that can be classified under the first, second, and third approach, the subtracting overshoots. Therefore, we need to add it back, and the process continues. This is the inclusion-exclusion principle. Suppose you are planning a trip from A to B. There are also places C and D where you might want to have a transfer at. Then this diagram shows all the different possible routes you can take, where different color represents different airlines. It is not as complicated as it seems. We can simplify the diagram by only recording the number of flights available from a point to the other. So the problem of flying from A to B can be done in the following approaches: direct flight, through C, and through D. Because you only take one of the approaches, we use the addition principle. If we know the number of ways to do the task using each of the approaches, we just add them up to get the final answer. Looking back at our schematic diagram, there is only one direct flight available. So the number of ways to use the first approach is 1. For the second approach, we have 2 subtasks to do. We need to first go from A to C, and then from C to B. Both subtasks need to be done to count as the second approach, so we need to use the multiplication principle. Going back to the diagram, from A to C we have 2 flights. From C to B we have 3 flights. So we have 2 and 3 in the corresponding positions. And we can put the product in the second approach. Now we can do the same thing for the third approach. Then this expression is the total number of ways to arrange a flight from A to B. This is an example of using addition and multiplication principle. Along the lines of planning a trip, let's pretend we are planning where the destination should be. Suppose we want to go there by direct flight, and there are 3 airlines that operate flights from our city. Airline A can fly you to 75 different destinations. Airline B can fly you to 27 different destinations, while Airline C carries you to 39 different destinations. To calculate how many destinations you can go, it is important to note that you only choose one airline for your trip, which makes the problem able to be dealt with by the addition principle. However, there are some destinations which are very popular, and 2 or more airlines operate flights to there. We have double counted these destinations when we simply add the numbers up, so we need to use the inclusion-exclusion principle instead. That means after we add those numbers up, we need to subtract the number of destinations where 2 of the airlines operate flights to. Let's say these are the number of destinations where any pair of airlines go to. Then we need to subtract these numbers. Finally, of course, there are really popular destinations where all 3 airlines operate flights to, and there are 5 of them. So we add back 5 and we can then calculate the result. This is an illustration of the inclusion-exclusion principle. You might be a little surprised that I didn't use Venn diagram to explain this principle because, first of all, drawing a Venn diagram for 4 or more circles is not easy. Another reason is simply that it does not aid understanding too much. You need to understand that the number of destinations that Airline A operates flights to is represented by this entire circle instead of only this region. So while Venn diagram is a visually appealing diagrammatic representation of what we are doing, I don't really like using it to make sense of what is happening. While we're at it, we could also see what permutation and combination are. They are not something new, but just some more sophisticated tools that can be derived from the multiplication principle, which we have seen earlier. Permutation and combination concern these situations where there are n different elements. You need to choose out of them. For example, this will be one possible choice. However, permutation and combination differs in whether changing the order of the choice counts different. For permutation, these 2 choices would be counted as different, while for combination, they would be counted as the same thing. Permutation, usually denoted as NPR, could be calculated as the product of n, n-1, and so on until n-r plus 1. This is because the first position has n choices. The second position has n-1 choices because one element has already been chosen. This process continues for all the r positions we have, so we end on n-r plus 1. The reason we use multiplication is that we have to perform all the subtasks of choosing an object in a position. For combination, we denote a little differently, n choose r. The only difference between combination and permutation is whether we count these different orderings the same. For each choice of our objects, the number of ways to move it around is exactly RPR. If we multiply the number of choices we have by the number of ways to order these R objects, we should get back NPR. Okay, so we have the permutation NPR formula as well as the nChooseR formula. We can now substitute the explicit formula of RPR and NPR in the first formula into the second formula. So we have this explicit formula of nChooseR as well. These formulae are rarely seen because writing these out is annoying. In order to write less, we denote the n factorial to be the product of the first n numbers. Why is this useful? Multiply the first formula by n minus r factorial on both the numerator and denominator. The numerator amounts to n multiplying all the way to 1, so it is n factorial. And so we can write the permutation like this, which is much easier than writing the entire product out. The same thing can be done to the combination formula. the numerator can also be rewritten as n factorial. In addition, this part of the denominator can also be rewritten as r factorial. So we have a simplified formula for n choose r. And so, we have constructed some more sophisticated tools based on one of the founding principles, the multiplication principle, with these formulae we derived. In the next video, we will focus on this particular scenario mentioned in the introductory video. What I haven't mentioned is that swapping two people borrowing money is counted the same, and swapping two people depositing money is also counted the same way of queuing these customers up. This video should make clear why whether swapping matters. So you can try to solve this problem until the next video, where I reveal how to come up with the solution. If you enjoyed this video, give it a thumbs up and share it. Don't forget to subscribe with notifications on so you don't miss out any new videos in the series. See you in the next video. Bye!